In this podcast episode, we're going to look at the introduction to chemical reactions, including the conservation of mass. One of the important things to realize when you're looking at chemical reactions is that all chemical reactions must follow the conservation of mass law. It states that the mass of substances that are present before a chemical change equals the mass of all the substances that remain after a change. In the picture, you'll notice the log burning maybe in a fireplace or a wood burner. Think about the chemicals that are involved in the burning of the log. We know that the log is going through combustion, so that means that the wood in the log and the oxygen in the atmosphere are reacting to produce the fire. After the log has reacted, it produces ash, soot, carbon dioxide, and water. And with the conservation of mass law, if we start with 5 kilograms of a log and oxygen, then we must produce 5 kilograms of ash, soot, and carbon dioxide and water, because we can neither create nor destroy the mass that was in our reaction. We can simplify this concept by looking at it in forms of an equation. If we take the mass of all of the reactants in a reaction, which is on the left-hand side of an equation, and compare that to on the right side of an equation, which would be the mass after the reaction, or our products, we can determine if, in fact, a reaction is following the law of conservation of mass. Let's look at an example. On the screen is an example from the textbook. It says 5 grams of hydrogen react completely with 177.5 grams of chlorine to form hydrochloric acid. According to the law of conservation of mass, how many grams of hydrochloric acid are formed? When solving a problem like this, it's best to write down what you know about each of the parts in our reaction. In the problem, it states that hydrogen, which is diatomic hydrogen, H2, contains 5 grams. Also in the problem, it states that chlorine, which is Cl2, diatomic chlorine, contains 177.5 grams. What we don't know is how much hydrochloric acid, or HCl, is formed. We can write this into an equation and solve for it. According to the problem, hydrogen and chlorine are reacted together, so that's on the left side of our equation. And we know that HCl are unknown, and we need to find that. That's on the right side of the equation. We substitute our chemical formulas for mass values in grams, and notice that HCl is carried out because we don't know it. And to simply solve this, we just add together 5 grams and with 177.5 grams. And we determine that HCl in this reaction would equal 182.5 grams. It's always important to keep in mind, why did we solve it this way? Well, we want to make sure that everything on the left side of our equation, the things that were being reacted together, are reactants. It's going to equal everything that's going to be our products, things that are being made. And as I rewrote here, you can see that the value for hydrochloric acid equals the value of the hydrogen and chlorine combined together. As I mentioned in the previous example, we have some very important terms that we use when we describe chemical equations. On the screen is a chemical equation. It uses CH4, which is methane. And when we combine methane with oxygen from the atmosphere, we can produce carbon dioxide, water, and a whole bunch of heat. When we look at a chemical reaction, everything that's on the left-hand side of an arrow is called the reactants. And everything on the right side of the arrow are called the products. The arrow itself, we use it as a reference, we call it yields. So we're reading like a sentence. The reactants yields the products. Just as in our chemical formulas that we learned about in the previous chapter, we see these subscripts in our chemical formula telling us how many of each element are present. Note that in the chemical equation, we have some new numbers that fall before a chemical formula. These are our coefficients. Coefficients tell us how many of each chemical formula are present, as in individual units, in a reaction equation. So when we combine methane with oxygen, we need 2 oxygen molecules to form 1 carbon dioxide molecule and 2 waters. They do not write coefficients in front of those chemical formulas where there's 1. It's just assumed that you know if it's printed there that it is at least 1 of those molecules. Now let's look at a sample problem that uses one of our chemical equations. We're looking again at methane combined with oxygen to make carbon dioxide and water. In the problem, it tells us that 75 grams of methane are reacted completely with 300 grams of oxygen to form 168.5 grams of water. The problem wants us to know how many grams of carbon dioxide are formed. The first thing we do is substitute our values. We know that there's 75 grams of methane, that there are 300 grams of oxygen, and 168.5 grams of water being produced. Rewriting our equation, we write 75 grams plus 300 grams yields carbon dioxide plus 168.5 grams. Just as we would in math class, we want to get carbon dioxide by itself, so we want to subtract both sides of our equation by 168.5 grams. And we find that carbon dioxide is equal to 206.5 grams. Remember, the whole purpose for solving the problem was to make sure our conservation of mass law was being followed. If on our reactant side we had 375 grams, that means we must have 375 grams on the product side. Since carbon dioxide equals 206.5 grams and water is 168.5 grams. If we add those two numbers together, we get our 375, showing that both sides of our equation are equal. Let's look at one more example. In this simple problem, carbon reacts with oxygen to form carbon dioxide according to the following equation. Carbon plus oxygen produces carbon dioxide. When 120 grams of carbon reacts with oxygen, 440 grams of carbon dioxide are formed. How much oxygen reacted with the carbon? First thing I want to do is write down the equation and then substitute the numbers for the chemical formulas. And just like in math class, I want to get oxygen by itself, so I'm going to subtract 120 grams from each side. And when I do so, we find out that oxygen equals 320 grams. In review, remember the conservation of mass tells us that matter can neither be created nor destroyed. That's why all of the matter that is present before a reaction has to be the same after the reaction. Even though the chemicals change, the mass, the matter that is contained in those materials must have the same mass. And we use the equation that can also be used as a chemical equation that the mass before reaction must equal the mass after reaction. This concludes this episode of the podcast.